So we had as our general finite element model for polar elasticity just try to put the matrices in brackets. Okay. All right, so these equations we derived in the continuum, sort of in the middle of the class. We derived them for fully finite deformations, and then we linearized them. And then we, a few weeks ago, just chose a Galerkin, well, developed the weak form, chose a Galerkin approximation, and this is the resulting equations, where you can look back in your notes for the definitions of M and Q and S. And of course, you should have some experience with them because you just solved a problem where you used at least Q and the stiffness matrix, which the stiffness matrix is, well, the stiffness matrix times U is what's in that integral B transpose times the effective stress, right? And so when we talked about, we also talked about like a modified beta method for solving these equations implicitly. And I wrote down that the tangent stiffness matrix was, if we define this to be R1 and this to be, well, define it to be R1 and this to be R2, then the tangent stiffness matrix that you'd use in a nonlinear problem to solve for the unknowns, the unknown accelerations and the unknown time derivative of pressure. Right. And of course, this only has this structure if, you know, we're solving some equation that's KU x equal to B, where x has the structure delta U delta P dot, right? But it should be clear that, and this isn't the case. Well, it depends on how you formulate your degree of freedom's correct, you know. But the way we did it, or when that day that I sort of went over that degree of freedom map exercise, it didn't have, this vector didn't have this structure particularly. You know, of course, in that it's a quasi-static problem, so it's just displacements and pressures, not the derivatives of them. But nevertheless, it didn't it didn't have that structure where all the displacements are grouped together and all the pressures are grouped together, right? They were sort of interweaved with each other, right? And so in that scenario, and it should be obvious that you can define, any sort of the tangent stiffness. If I just say that the a residual R is R1 plus R2, where, and then X is whatever it is, whatever it is, depending on, it could be your choice, U of X at node 1, UY node 1, P node 1, U X at node N, U Y at node N, P at node N. And this is what, at least if you followed my example in that degree of freedom map thing, this is sort of the structure we had, right? Then the residual, or the tangent stiffness matrix, is going to be the partial of the residual with respect to X, right? Or if we do it via finite differences, it'd be like Ri X plus delta Ej minus Ri X over delta. So remember, the residual is a vector in this case. It's a vector. And so the ith component of that vector, so it takes the ith component of vector of the residual R is a function of the vector X, right? And so then if we perturb it by some unit vector, and we talked about what this is. So this will be a finite difference approximation. So anyway, so we have this residual vector, and we can construct a tangent stiffness matrix like that, and we can use it in a gradient-based Newton-type iteration, okay? But we can also just, another sort of approach, and something you may want to try, it might be fun to try on your little one-element problem you're working on this week for the plasticity problem, is that we can just we can basically use any method from optimization, right, by defining an objective function that we want to minimize, right? Well, this residual should be 0 if it's in equilibrium, right? So we could compute some norm of this thing, right? An L2 norm is probably adequate. You can compute some norm of that thing and call that our residual. So maybe you call it, little r is equal to the L2 norm of the vector r. Just to be explicit, these are vectors. And also, I'm not sure how to indicate it correctly, but keep in mind that when you do this, right, these need to have the same size. So up there where you have vectors of pressure and displacements, they need to have the same structure as X. They'll just be filled in. They'll just be, obviously, Q times some pressure, it'd really be Q times X, but there'd just be zeros where those guys are. So that ultimately, in order to add them together like this, they have to be the same length. Right? But ultimately, right? And then in that case, then you can construct your tangent this way, right? But back to what I was saying, you might just define some objective function and then use some method from optimization. And the reason that you might want to do this is because this thing can be really expensive for large problems. And we talked about that with graph coloring and tricks you can do, right? But there's also a class of methods called like Jacobian free Newton-Krylov methods, right? So Jacobian free Newton-Krylov methods. And in these methods, you know, most iterative methods, you multiply, right? You multiply the Jacobian sometimes on some vector, some iterative vector that you're iterating on, right? And you use that to reduce the residual, okay? So this is like, you know, these are subjects of a numerical methods class, right? But basically in any type of iterative numerical solver, you have your Jacobian and you're multiplying some guess at the solution vector and using that to update the new guess and over and over and over again, okay? And of course, that you have to construct the Jacobian to do that. Well, these Jacobian free Newton-Krylov methods basically use, since every time you're doing like a matrix vector product operation, instead of constructing the Jacobian itself, they basically just do this step for 1j and immediately multiply the vector, and so they don't actually construct the full Jacobian, right? So, you know, so they would just, you know, for all, you know, all I and say j equal to 1, they do this operation. Now you just have a vector, and then you do the matrix vector product, and you'd store that instead of storing the whole Jacobian, and then you do it iteratively. And the Newton-Krylov, the Krylov, they use the special subspace for the update the guesses and other things. But it's not really, you know, it's not a class in numerical methods. If that interests you, you should take a class in numerical methods. But basically, we're engineers, and we're just going to use these type of methods as solvers for the problem. Anyway, there's other methods like Broadens Method, which, you know, in Broadens Method, you actually do compute this once, but then you know, a full straight up Newton method, you would recompute this guy every Newton iteration, right? And that's really expensive. So, a method like Broadens Method, you'd compute it once up front, and then there's this technique that you can just update it every time. And so then it becomes like a, well, it's Broadens Method, but it's a quasi-Newton method where you're not redoing that every single time. But so, you know, you guys are programming in MATLAB or in Mathematica, or Mathematica or maybe Python. And so to get access to these type of things, you can't just, if you just call fsolve on this, right, or you know, on the residual, if you just call fsolve or one of the optimization routines, fmin, search, or whatever, they're going to, if you don't do anything, it's going to finite difference the residual. It's going to find a difference in the residual and compute a Jacobian if you don't do anything at all. And well, MATLAB will. So who's using? Most of you using MATLAB, right? Right. So MATLAB, yeah, a couple of guys using Python. Okay. So yeah, in MATLAB, I mean, have you ever dug into this to the fsolve and like played with the options of it? You're going to have to if you want to use this method and or you know, these type of methods. And so it's kind of hard to get that all on the screen, but you know, probably one of the better things you can do is to use the trust region reflective method, and then certainly use the Jacobian pattern. So what the Jacobian pattern does is, because this is something we actually know in a finite element code. So what the Jacobian pattern does is basically the graph of the matrix, okay? So this is your connectivity pattern. Of course, you have to remember that every node has 3 degrees of freedom, right? But you know, you can basically figure out the connectivity in the sense that, and it explains it here, right? So the sparsity pattern Jacobian for finite differencing. Set Jacobian pattern ij, so the ij entry of the Jacobian. What they're saying Jacobian, what we call tangent stiffness matrix, right? So set the Jacobian pattern ij to 1, basically, well, it's easiest understood if you just read this sentence. In other words, Jacobian pattern is equal to 1 Jacobian pattern is ij is equal to 1 when you have the function that computes the tangent stiffness matrix at the entry ij not equal to 0, right?